Good morning, Justin, Ian, and Deanne.
Morning, Al.
Morning,
How's
Alan.
everything going?
Good.
It's all right. How are you?
Not too bad. I hope you guys are socializing a little bit and not just, not in an electronic way. I hope you guys are seeing human beings and interacting. So, time to
A
get
little
healthy.
bit. Probably not this week. Finals and everything.
Yeah, but it's important to see people, in flesh live. So, hopefully, that's happening at parks or at walkways or jogging or
Yeah,
probably next weekend is a good weekend to go to the beach, or in 2 weekends when you guys are done with all your schoolwork. So
that's a good idea.
get
New
out
golf
and
courses are open, so that's nice.
absolutely get out and put some sun in motion and enjoy some sun somewhere. Weather should be collaborating with us in June. But anyhow, how is chapter 9 going? Was chapter 9 pretty much okay? Is there anything you want to go and review before we hit chapter 10? Any chapter 9 questions? So this afternoon, I don't have meetings. This afternoon, I'm here from 1 to 4. So I'll start a little early. I'll start at 1, not at 1:30. I'll make that modification and I'll stay till 4. And I'll do the same tomorrow. So that if you guys have questions about the chapters that you're involved in, or past or present, okay? So today's session for Q&A 1 to 4. Okay. Do you need an invite for that? Do you need me to resend the invite for that session?
Is
Yeah.
that session gonna be on this Zoom or it's on a different Zoom?
It's a different Zoom. The sessions for afternoons are different than the morning ones. So let me go back and look for the Zoom calendar. There it is. Copy. Okay. And paste. Okay, so I sent it via chat, the invite for today. I'll try to be in that room at 1, and if not shortly thereafter. So that's for this afternoon in terms of Q&A. And let me share with you the items for today. So chapter 10 notes. So I noticed that some of you referred me some students in the summer, so I appreciate that. I'm full, and actually the sections that I have for the summer have a lot of extra interest, so I'm gonna allow people to add since it's online. The school didn't want to give me budget for another full section of students, so I'll just add them to my classes like I've done in the past. If you have friends who are starting college in the summer, try to spend some time teaching them how to use Canvas a little bit and teaching them how to use Zoom a little bit, give them some advice on that, because that's one of the biggest problems when people are entering high school, from high school or from college or from a non-college environment. It's really hard to get accustomed to the Zoom and the cameras and to Pearson as well. So if you have friends in that situation, it'd be really nice if you help them a little bit. Under document sharing exam 4 module, there is a exam 4 notes on chapter 10. So I'm going to open that file and I'm going to update it, and then I'm going to reload it when we're done with the session today. So again, it's called exam 4 notes on chapter 10. There's also notes on exam 4 for the 3 chapters, 9, 10, and 11. And between those notes, you have a complete guide to helping you with any and all exam 4 questions, and also any and all lab and quiz questions for all chapters in there. The notes that I hope you can see now are the notes on hypothesis testing. Again, we're still talking about percentages of a population in a categorical data environment. So we're talking about the fraction, a characteristic that is contained in the fraction of a population. And then we're talking about developing something called a hypothesis test. And hypothesis testing is how we implement deduction or deductive reasoning in statistics. So it's a form of inference where you use deduction. And deduction means exactly what the word deduction means. Deduction means to take away. So deductive reasoning, deductive reasoning is a way in which you reduce your information sets, which come in many varieties, you reduce them into a conclusion, okay? So in hypothesis testing, there are four components of a hypothesis test. So we're going to describe those. And after we describe the 4 ingredients of a hypothesis test, we're going to go on to show how we reduce those 4 components into a single number called a p-value, which is a probability. And that probability value is the one that allows us to decide whether the theory that we're interested in testing is going to be a theory that passes that test or that fails that test. It's going to be a theory that we do not reject or that we actually do reject. So I'm opening a whiteboard right now to show you the process of testing. And I'm going to go back and forth between this whiteboard and the notes. So if at any time you see me sort of flailing and doing that switch, try to remind me, hey, Alan, you're making a fool out of yourself. You don't seem to notice that you're in the wrong part of the handout. So, okay. So let's go back to the notes first. Our notes on chapter 10. And again, hypothesis testing is a procedure where we test a theory. And the main theory is called the null hypothesis. And it must be a theory that has an equal sign. Like, for example, I could have a theory as follows. 17% of DVC students transfer each year to 4-year universities. And then the way we would write that theory, the original hypothesis or null hypothesis, is an H with a 0 subscript. And we would say that the purport P equals 0.17. So this P equals 0.17 is the same semantically as saying 17% of DVC students transfer each year. So every time you decide that you're going to test a theory, the theory that you physically call the original hypothesis of the procedure must have an equal sign. It could be the full equal sign, it could be an at least, or it could be an at most, but it's got to have an equal sign, an equality, so that you can write it as you see in the handout. Okay, so the null hypothesis is one of two theories. And it is that P equals some given value. So we're going to call that given value P0 generically. So you have a theory. The theory is, in this case, 17% in the problem that we're using as an example. And that hypothesis is going to be tested against some other alternative theory. Hypothesis testing is a procedure in relative truth-telling, not absolute truth-telling. Facts are only temporal, so you could test a hypothesis today and retest it a month from now, and you could get opposite results. And that stands to be the case in situations where you have fluctuating percentages. And so you're trying to establish if something that was true perhaps remains true, or if the world has changed. But it's not a procedure. Hypothesis testing is not a procedure that establishes some absolute truth that is always eternally true. So the null hypothesis is always set up in the form of an equation where the percentage of a characteristic is some given value. And then we're going to need to test that versus another theory. And the opposing theory is called an alternative hypothesis. And the alternative hypothesis is usually an H followed by a number 1 or a letter A. And there, the proportion in question under testing will either have a not equal sign or a greater than, strictly greater than, or a strictly less than. So it's going to be one of those three. One of these three inequalities. And the null hypothesis must be stated as an equality, partial or full. Okay. Hence the name hypothesis testing. It's really a competition between two theories, an original theory, a null hypothesis, or an alternative. So those are the two main components of your test. The next two components of the test are what enable you to process through and reason through your your hypothesis. Notice that the null hypothesis is a theory, a belief, a hypothesis. So we're going to call this a belief for now. The null is what you believe in when you're testing something. Now, what do we usually compare our beliefs to when we are thinking? Usually we compare our beliefs to something that we see. Okay, so seeing and believing are the two components that we use in building tests. We're basically going to take what we see and compare it to what we believe. What do we see in statistics? What we see in statistics is data and statistics from data. What we see in the case of proportions is we see a number of trials of some sort, and then a number of successes. So what's different about data is that data is observable, and it should also be replicable. You should be able to see this, to see data, and someone else should be able to peer review your work. Somebody else should be able to also see like data and make their own observations and test your hypothesis test and confirm it or reject it so that your theories can be subject to scrutiny. Okay, so in this case, we need to have random sampling available. The observation should be independent. You should have less than 10% of the population of data. And you should have at least 10 successes and 10 failures. So those 4 conditions are the 4 conditions that your data must abide by for purposes of replicability of your testing, of your hypothesis test. If your data obeys those 4 rules, then you can come up with something that you see that we call a sample proportion. And a sample proportion is what you get when you divide the number of successes by the number of trials. And so one of the great things about being able to see a statistical proportion from a sample is that you can then compare it to the hypothesized proportion. And you can make that difference, you can convert that difference into a z-score, into a standard deviation unit object or statistic, into a location statistic. And you do that by dividing this by the square root of the sampling model in question. And the sampling model in question is, thanks to these 4 conditions, the sampling model in question is a normal model. So the normal probability model, the normal sampling distribution, is what we use to test hypotheses in proportions. And as a result of that, this being a normal model, then this is called a z-score, or a z-statistic, z-test statistic. In a normal setting. And as we all know, if we know of a certain cutoff, these were called cutoff points in chapter 7. A test statistic is a cutoff point. Is a range of z values that measure the difference, measure the statistical difference between what is seen and what is believed, between seeing and believing. So that's the job of a test statistic. The job of a test statistic is to measure how far what we see in the data is from what we hypothesize according to the null hypothesis. And so you take this test statistic, and you embed it into a normal model, into a normal distribution. Additionally, you get some help from the alternative hypothesis here. As we know, the alternative is expressed in the form of an inequality. So if you see an alternative hypothesis where the sign is a greater than, then we cut off the right side of the model, the right side of the normal distribution. If, on the other hand, we see less than in the alternative, then instead of cutting off the right side of the model, we're going to cut out on the left side of the model, left side of the normal distribution. And that usually implies that you're going to see a negative z-score on the test statistic, because less than in the context of a normal model means below average. And when you see a hypothesis where the sign is not equals, then we cut off on both tails of the normal model. And we use that we use this information combined with the test statistic to calculate what we call the p-value. And a p-value is a statistic probability that what we see in the data supports the null hypothesis. So it's a probability, it's the odds in favor of the null hypothesis. That's what a p-value is. It's the probability that your data confirms the null is the better theory. And in StatCrunch, to get all this work done, takes one line of command. Stat proportion statistics, one sample with summary, and then you tell the software what the number of successes are, and you tell the software what the number of trials are, what the number of observations are, and you select to perform a hypothesis test. And you then click on compute, and you're done. Oh, sorry. When you perform a hypothesis test, you have to clarify the value of the null hypothesis. And you also have to clarify the direction of the alternative hypothesis. So you have to pick greater than, or less than, or not equal.
Unequal.
Not equal, yeah. And after that, you click on compute. So that's
Should I get a snap of this?
so that's how you that's what you get from StatCrunch. You get all this worked out up to the probability value of the test, up to the p-value of the test. So what I'm going to do is I'm going to take this particular paint and I'm going to put it in our notes. So what you get out of StatCrunch is a probability. And then the last step is you compare the p-value that you get from the hypothesis test, the p-value from StatCrunch, to the significance level of the test. And the significance level is the fourth ingredient of the hypothesis test. Notice how the graphic above has a green box and two red boxes. The green and the red box combine into the black box of the z-score. And the z-score and the alternative combine to form a p-value. So notice why we call this deductive reasoning. We're calling it deductive reasoning because we're reducing these pieces of information into fewer and fewer pieces until we just get one probability. And this one probability is compared to the so-called level of significance, which in your textbook is expressed in the form of the Greek letter alpha. And this is, the significance level is given as part of the test, as part of the hypothesis test. So this alpha you get in language of the question. This is not something that you have to compute or figure out. Alpha is given. So here's an example of a question. 17% of DVC students transfer to four-year schools. That's what DVC believes. So what do we call that? The null hypothesis. Recent data suggests that the transfer rate might be declining. What does declining mean? It means that instead of the transfer rate being 17%, it's less than 17%. Okay. So this is the null hypothesis that P is 17%. And this implies an alternative hypothesis that P is declining, meaning it's less than 17%. So the first two sentences of the question here give you the null and the alternative hypothesis. A consultant to DVC takes a random sample of 400 students and finds 60 are transferring. So that's your data. At the 5% level of significance, so that's your alpha. What is your conclusion? Is DVC still transferring 17% or is this transfer rate in decline? Okay. So notice how we get the four ingredients of a test. We get the four ingredients of a test. So what do we do in StatCrunch to answer the question? We go stat, proportion statistics, one sample with summary. We put 60 as the number of successes, 400 as the number of observations. We leave the perform dot under hypothesis testing, and we set the null to 0.17, and we set the alternative to less than 0.17. In other words, out of the 3 possibilities, we pick less than out of the alternative hypothesis we put these, that's how the ingredients look. And when you click on compute, you get these results. You get these results that are here. And you get all the way to the p-value, from the test statistic to the p-value. So the software takes the 60, the 400, creates the sample proportion, finds the amount of standard deviation in that sample proportion, calculates how different the data is from the null hypothesis, and it calculates what probability there is that the null is the better of the 2 theories. So it finds that there's a 14% chance that the null is true given what you see in the data. And that's enough to actually keep the null hypothesis, because our probability of reasonable doubt, our probability of rejection, our significance level is 5%. Okay. Since our reasonable doubt probability is 5%, and 5% is smaller than 14, the p-value ends up being greater than alpha. So we cannot reject the null hypothesis, which means that 17% is still a reasonable belief about DVC's transfer rate. So we couldn't disprove that DVC's transfer rate is in decline. We cannot say that DVC's transfer rate is in decline. And that's how we interpret the results. Of a hypothesis test. The notes also have another approach called the statistic approach to solving these kinds of hypothesis tests. And it does so calculating what's called a critical score. And I'm going to cover critical scores in the session from Monday of next week. And the other way to read the conclusion is in your notes. And instead of talking about DVC transfer rate, I do another example here where we're looking at Procter & Gamble and their customer brand loyalty to Crest toothpaste. So I'm going to now go into lab 10, quiz 10. And this is this file is going to be called Exam 4 Notes on Chapter 10, Hypothesis Test for Proportions from May 13, 2020. And what I'm going to do with these notes that you are looking at right here is I'm going to upload them. I'm going to upload them to your notes. So they should be at the very top of your notes, right above the chapter 9 notes that we uploaded on Monday. So let's go into assignments now. I'm going to go to exam 4. The first 3 questions on exam 4 are questions from chapter 9. They are about sample size. So we learned how to compute sample size on Monday. They are about confidence interval. Where we learned how to calculate a margin of error. By subtracting and by adding a margin of error from an initial estimate, we get the confidence interval. We also learned how to compute confidence intervals and now in questions 4 and 5, we're going to be applying chapter 10. And in questions 6, 7, 8, and 9, we're going to be applying chapter 11. So exam 4 has questions from all 3 chapters, 9, 10, and 11. And the 2 questions that are from chapter 10 about hypothesis testing are questions 4 and 5 on your test. The question 4 starts, one study reports that 34% of newly hired MBAs are confronted with unethical business practices during their first year on the job after they graduate. What that means is that either E is true, or D is true, or F is true. But A, C, and B cannot be true. B can't be true because nulls never have signs other than equal signs. And A and C can't be true because the study that we are starting our analysis from stated that the proportion that we're testing is 34%, not 29%. So that's how you start simmering down from 6 options down to 3 options. One business school dean wondered if her MBA graduates had similar experiences. Can she conclude that her graduates' experiences are different? So that different is what tells you whether it's a, notice that the question is not, can she conclude that her graduates' experiences are greater or are lesser? They don't point to one side or the other. And then immediately they ask you, what is the test statistic? So here you put a z-score. What is the p-value? So here you put a probability. And then what's your conclusion? Well, your conclusion is based on comparing the p-value that you get in your test to this 5% here. If the p-value is greater than 5%, you fail to reject the null. And if the p-value is smaller than 5%, you reject the null. So that's how simple it is to go through a hypothesis test question like this one, and also like question 5 as well. So both questions 4 and 5 follow the processes that we've been looking at in the notes that I just uploaded into your system. So let me share with you lab 10. A poll of 1,048 investors states that 62% of investors say that the federal budget is hurting the investment climate a lot. Is there any evidence in that data that the percentage has decreased from the 73% that it was before the climate change, the investment climate change? So in this case, equals is the null, less than is the alternative. And the test statistic is going to compare the 62% observed to the 73% hypothesized in units of standard deviation. But you don't have to do the math on this test statistic, because what you can do is open question help, StatCrunch, and when you open StatCrunch, you go stat, proportion statistics, one sample with summary, the number of total observations was given in the problem earlier. It was 1,048 investors. Of the 1,048 investors, apparently 73% were thinking the investment climate was not good. So the way I write the number of successes is by multiplying the percentage of successes out of the sample size. The null hypothesis is the percentage in the earlier study. And the alternative hypothesis is defined by the choice of one of the three symbols. In this case, the less than symbol is the one that we are using. Or is it the greater than symbol?
I got 69% and 83%.
Okay. But is it has fallen from from 73%, and this is 62% in my case, okay? Has fallen. So then the test statistic is right there. Can you see the test statistic? I hope so. So when we go back to the homework, this is this answer is -8. In other words, the difference between 62% and 73% is 8 standard deviations. 8 standard deviations below.
Alan, could you go back to StatCrunch for a sec?
Okay, so this -8, again, comes from comparing 62% to 73%.
Did you say the 73% of the investors are saying that the federal budget deficit is hurting, or is it the 62% that's
73 in my case was the earlier percentage. And
Okay.
62 was what the data showed. So the 62% is what gives you the number of observed data in the data successes. And the 73 was the null hypothesis.
okay?
Where that's going to make a difference is in the sign of the test statistic. Had I gotten this wrong by confusing the sample proportion and the hypothesized proportions, I would have just gotten a +8 instead of a -8. So I would have gotten the part of the distribution that I'm looking at incorrect.
Hey, Sam.
So I'm looking at something that is not even close to real, because the chance that I see a z-score below 8 is nearly impossible. That's what this p-value means, that there's almost no chance that this null can be supported by this data. This data is more consistent with the alternative, so we have to reject the null. Because 62% is 8 deviations different than 73%. So there's no chance the null can be true. If what you see is something completely unbelievable relative to what you believe, then you typically throw away your belief, because you're seeing data that is just impossible that it could be consistent with the null hypothesis, with the belief in your null hypothesis.
Using just your z-score would be impossible trying to find the
8 deviations in a normal model is an outlier, is another way to think about it. An 8 deviation difference is an outlier. Now the critical value, a critical value is when you convert the significance level, the alpha, into a z-score. That's what a critical value is. And to do that, what we do is we just set this area here to the level of alpha, which is 5% in this case. And that gives us a critical score of -1.645. Meaning, if your null hypothesis is more different than your data, is more than 1.645 deviations different than your data, then that red zone is the 5% of the time that you are willing to reject the null hypothesis. Okay, so that's how you convert a critical value, an alpha, into a critical value, a percentage probability into a z-score.
How did you get that?
In the normal calculator,
Yes. Both of these things, the 0.05 and the negatives 1.644.
I didn't get, this is what I got. So this is what I don't know. And what I do know is that this number represents my alpha. So whatever my critical value is, I put it here. In this case, 5%. And then I click on compute to solve for the unknown z-score. And this 5% came from
The question itself for the 5% significance level. We're
correct.
trying to find a critical value.
That's where the 5%, it says compare the z-score from part A to the critical value associated with a 5% level of significance. And so this is how I know that this is minus 1.645. The z-score is less than the critical value. Minus 8 is smaller than minus 1.6. So we have to reject the null hypothesis because there is a lot of evidence that the percentage of investors has decreased from 73% to 62%.
Hey, Alan.
Yes, sir.
How did you get the critical value again?
Okay. So the first question was, what is the null hypothesis, right?
Yes.
So the null hypothesis tells you what the original belief is. Also, you want to know what this is going to compete with. So you want to know what the alternative hypothesis is. And that is less than. And the reason that this is less than is because you're looking for the possibility of decrease from 73%. Okay, so this is a less than. And then when we find the z-score, the z-score that's called a test statistic is going to compare the 62% observed to the 73% believed in units of standard deviation of the model. And in our case, that was a -8, meaning that 8 standard deviations separate 0.62 observed from 0.73 believed. The critical value, a critical value is the tolerated number of standard deviations given the level of significance of the test, which is also known as the level of reasonable doubt, which is a given in the problem. And so the way we calculate that is from the standard normal model, from the standard normal calculator, where the area is on the left tail of the model. And that's because the alternative hypothesis has a less than symbol. And the area in the left tail equals alpha, which in this case equals 0.05. So the critical value becomes calculated as minus 1.645. So -8 is less than minus 1.645. That's just basically saying that the test statistic is smaller than the critical value. The critical value comes from the normal calculator. The test statistics come from the hypothesis test. And we're rejecting the null because of the fact that the test statistic is smaller than that. So that's what tells us that the best conclusion is to reject the null hypothesis in favor of the alternative. So to go over the explanation, test statistics come from the hypothesis test. comparing sample proportion to null hypothesis proportion. The critical score comes from alpha and the direction of the alternative hypothesis, and is obtained from the normal calculator. So it's not something you calculate, it's something that you find based on the alpha of the model and on the alternative. The test statistic comes from the data and the null hypothesis. The critical value comes from alpha and the alternative. And then when z-test in absolute value is bigger than the critical value, you're going to reject the null hypothesis. Otherwise, when the absolute value of the z-test, when it's the other way around, you're gonna do not reject the null. And those are your rules for decision making. Okay, so in this case, we were working on lab 10, question 4, right? So I'll put these notes as well as the earlier notes that we did on the chalkboard inside these exam 4 notes on chapter 10. And I'm gonna upload them to your document sharing. So it has those notes as well. So the notes from both of these boards from board 1, the theoretical notes on the process of p-value, and from board 2, the notes on how to calculate test statistics versus critical statistics so that you can then get the conclusion. Both of those notes are now embedded in your exam 4 notes. Both of those are embedded in, you know, a place where you can download it right away. We have 15 minutes left. So I was wondering if you had any questions.
Can we go over lab 9, Alan?
Sure. What question in lab 9?
Question 5 and 2.
Okay. So in question 5, you have a national average of 74% of college students staying between their freshman and their sophomore year. There's a certain college where the retention of freshmen is 510 out of 595.
I
So
don't think we can see the lab screen, Alan. I think it's on your, oh, there we go.
Cool, thank you. So you're comparing a national average of retentions of students of 3/4, more or less, to what's happening at a certain college, which is a much higher rate of freshmen return to their second year of college. A lot of times at 4 years, there's a lot of partying in their first year. And if students sort of don't accommodate to the environment quickly enough, they end up partying too much, and about 1/4 of freshmen in the country drop out in the US. Or they're dropped out due to academic probation matters or medical reasons or a bunch of different reasons. But there's a particular college that, according to the data, has 510 people returning as sophomores out of the 595 who started. So the question is, does this college have a right to brag about their retention rate? And the answer is yes, because there's more than 6 deviations difference between 74 and whatever this rate is. So the idea here is that if you go to StatCrunch, and please remember these two numbers, 510 and 595. And I go stat, proportion, one sample with summary. Again, stat, proportion statistics, one sample with summary. And I have 510 returning sophomores out of 595 freshmen. And I build a confidence interval, say of 95%. The percentage at this school who are returning is 83% to 88%. So when I look at the model, at the normal model that's behind this confidence interval here, and I set the mean to 74%, because that's the national average, 74%, and the standard deviation is 0.0143. That deviation comes from here. and I look at how far 510 out of 595 is from that, I can't even compute it, because the number of deviations from 74 to 86%, it's off the charts. It's 1, 2, 3, 4, 5, 6. It's more than 6 deviations different. There's no way that this college is like the average college. And then number 2 is a question about sample size. And the sample size formula from your notes from Monday require that you find a z-score and that you square it. The z-score comes from the confidence level, and that you divide it by a margin of error, and that you multiply times P and times Q. So here, P and Q are based on the fact that 25% of college students own their own car. That comes from the study that's listed there. The margin of error is 2%, according to the information given in the problem. So you want to estimate the margin of error within 2%. And being 90% confident means that your z-score is going to come from a normal model. So this 90% here comes from a normal model where you want to cut the 90% of the middle of the model, and that's where you get plus 1.645 and minus 1.645. And so
Can't see it.
That's how you get the z-score from. That's how you get the z-score with a 90% level of confidence. You're basically cutting 90% of a normal model, and you're seeing how far that is in units of standard deviation. So that's how you get those critical cutoff points. That's how you get your z-score. So once you have your z-score, once you have your z-scores, and once you have the margin of error entered in the right place, and the proportions P and Q come from what's given in the problem, then you do the arithmetic on this. So you're going to multiply and divide all this. Data, compute, expression. So it's the z-score squared times P times Q divided by the margin of error squared. That's your sample size. So I get a sample size of 1,269 observations. So this is lab 9, question 2. Where you have the z-score to the power of 2 divided by the margin of error to the power of 2 all of that times p times q. And in this case, it's a 1.645 squared divided by 0.02 squared times P times Q. And that's 1,269. And that's the answer to the question.
I got 98% confidence.
Okay, so then your z-score is going to be different. Your z-score should be 2.33 because you're going farther out on the tails of the normal model to get that. So that's the answer to the question.
Hey, Alan,
Yes,
are you going to be posting the recordings from today?
I'm sorry, could you repeat your question?
I asked if you were going to be posting the recordings from today.
I should. It's just posting the link. So yeah, as soon as it gets ready, I'll post the link from Monday and the link from Wednesday.
Cool.
So this is our board work here. Did that make sense for the person who was asking about the sample size question?
Yeah, that made sense. Thanks, Alan.
Welcome, dear. Okay, guys, I'm gonna take off and I'll be around this afternoon. I sent you by chat the link to our afternoon time for lab hour consultation time. And I'll see you shortly.
Thank you.
Thank you.
Thank
I'll
you.
join this afternoon.